Hello dear students. In this session we will discuss about GH effect. That is GH effect means Gordon-Hess jitter. It is discovered by Gordon-Hess. That is why it has got the name GH effect. The Gordon-Hess jitter is a timing jitter that originates from the fluctuations in the sender frequency of any waveform. Suppose we can say this jitter has been greatly influencing the long haul fiber optic communication, basically that is based on soliton systems, and this jitter causes variations in the output, and usually jitters are undesirable in any communication systems because it generates noise in the communication system, and there are several mechanisms that cause timing jitter in a communication system. So that may be either due to pulse generations in the laser when it produces a light output, or sometimes it may be due to the propagation laws in the optical fiber, or that may be due to the propagations that may be entered into the system when the light wave propagates through the optical fiber. Gordon-Hess effect is due to the combination of fluctuations in the central frequency of optical pulses with the timing. Therefore, the change in the central frequency causes a change in the group velocity of the light pulses, and which in turn affect the pulse timing. Gordon-Hess actually made analysis based on the soliton pulses when it is propagated through the long haul data transmission channel, and Gordon-Hess considered the noise in the fiber optic link with the periodically spaced fiber amplifiers. That is, the analysis of this Gordon-Hess effect is made through the optical link with the help of the amplifiers. That means in the link there will be different amplifiers are placed. In these amplifiers, it is assumed that they have a wavelength independent gain, and that introduces a quantum noise in the communication systems. Usually you know that in the case of amplifiers, you know that there is a noise chance, that is amplified spontaneous emission noise, like that. Usually when we are placing amplifiers, we are assuming that that has got an independent gain, wavelength independent gain, and that introduces a quantum noise, and this noise randomly causes a shift in the optical central frequency, and with more and more shift in the central frequency, and the timing deviations of the pulse will accumulate. That means there will be timing deviation of the pulses that we will receive, and this accumulative effect of these deviations causes the timing errors. That means the timing errors will grow with the time, and this type of jitter, or GH type of this jitter, can be suppressed by using regularly spaced optical filters or amplifiers that is having a limited gain bandwidth. And usually the mean square fluctuations of the soliton positions depends upon the soliton parameters that include the half width, full maximum power, and also the soliton spacing, etc. And so that we can minimize this effect by properly adjusting or these parameters, soliton parameters, so that we can adjust, we can suppress the Gordon-Hess jitter. Next, we can do a problem in soliton link design. The question is, design a soliton link to transmit information at a rate of 10 gigabits per second over 8600 km trans-Pacific soliton link. Given the dispersion length, L dispersion is equal to 100 km. It is in the it is the smallest value, and the dispersion factor D is equal to 0.5 picoseconds, and it is at a wavelength of 1550 nanometer. So you are asked to design a soliton link. So you should know the soliton link design equations that we have discussed in the last class, and it is required that you have to transmit data over the Pacific Ocean, and that is up to a range 8600 km, and the data rate is 10 gigabits per second, that is capital B. That is the data rate, that is equal to 10 gigabits per second, and total transmission distance is 8,600 kilometer, that is LT is 8,600 kilometer, L dispersion is 100 kilometer, and dispersion factor D is equal to 0.5. These all are the parameters you are given. Also lambda is equal to 1550 nanometer. So here we will make a substitution. We will make an assumption that here data rate is very high, that is 10 gigabits per second. So we have to select a suitable value for S0, which is spacing distance of the solitons. Let it be S0 is equal to 8. So first we have to find out the oscillation period for the soliton, and it is given by the equation omega equal to pi by 2 into e raised to S0. Pi is 3.14 and S0 is 8. So we will get the value of omega as 4680. So also we have given the dispersion length as 100 kilometer, that is L dispersion is equal to 100 kilometer. So we have to check different conditions for the soliton link design. First condition is that interaction distance between the soliton should be very greater than the total transmission distance. Here total transmission distance is 8,600 kilometer, and we have to find the interaction distance. Interaction distance is obtained by the equation omega into L dispersion. Omega we have find out it is 4680 and L dispersion is 100 kilometers. So we can substitute here. So we will get the value as 4.7 into 10 raised to 5 kilometer is this value, that is interaction distance. And we have LT value is 8,600 kilometers. So we have to check whether this condition is satisfied or not. Here you can see that this condition is satisfied. That means the interaction between the soliton should be very greater than the total transmission distance. Here that's true. Actually it is 33 times higher than the 8,600 value. So next we have to go for the condition, that is b square LT is very less than 2 pi by S0 lambda whole square into C by 16D into e raised to S0. This is another condition for the soliton link design. So we have quantities S0, lambda, C and D and S0. So we can substitute here, so that we will get the value of b square LT will be very less than 2 into 10, 3.14 divided by 8 into 1550 into 10 raised to minus 9, since it is in nanometer. So we have to convert it into meter, that is 1550 into 10 raised to minus 9 whole square into 3 into 10 raised to 8 into e raised to 8. Actually I forgot to put the e raised to 8 here. So we will get b square LT will be very less than 2.87 into 10 raised to 7 gigabits per second square, gigabits per second square. So for the 10 gigabits per second data rate, the transmission distance should satisfy the conditions. See here B is given in the question, that is B is 10 gigabits per second. Then we have to find out the condition for LT, that is LT very less than this quantity, that is 2.87 into 10 raised to 7 divided by b square. B is 10 gigabits per second. So 10 means 10 into 10 raised to 9 gigabits per second, 9 bits per second. So we will get LT will be very less than 2.87 into 10 raised to 5 kilometer. That is another condition. Here LT is 8,700 kilometer. And the total transmission, and that is LT is the total transmission distance, and that will be LT will be very less than 2.87 into 10 raised to 5 kilometer. So the condition is satisfied. See, you can you know that 8,600 is very less than this quantity, right? So that condition is satisfied. Next, in the third step, we have to find out the soliton pulse width for full width half maximum condition. That is soliton pulse width has the equation B is equal to, this is the equation, that is 1.7627 divided by 2 S0 into TS. That is obtained from this equation. So we will get the value of TS, that is soliton pulse width TS is equal to, we can rearrange the equation, that is 1.7627 divided by 2. S0 is 8 and B is 10 gigabits per second, that is equal to 10 into 10 raised to 9 bits per second. So we will get 11 picosecond. Soliton pulse width is this one. So next we want to find out in the design procedure, we want to find out the fraction of the bit slot occupied by the soliton when S is equal to 8. So fraction of the bit slot occupied by the soliton is obtained by TS by TB, that is given by the equation 0.881 divided by S0. So we will get the value as 11%. So thus we have designed a soliton link. These all are the parameters which we want to find out in designing a solitons. That's all about this topic. Thank you.